right, so I always get a haircut that conveys zero knowledge about where my bald spots are before I talk about zero knowledge. So, okay, so let me give you a small outline of the talk. First, I'll start with some simplified details about the Aztec smart contract system. This will lead us to define a notion called repeated computation with global state. Then we'll go over how to deal with global state using log derivative methods. And I'll end by highlighting a theoretical issue I want theoreticians to look into. So Aztec is about private smart contracts. So like Ethereum, a contract has functions, but since everything is snarkified, every function, say A and B, have some verification key that matches the function. And what can functions do? Well, one important thing they can do for this talk is that they can call each other. A function can call a function in the same contract or a different contract. So let's spend a few minutes thinking about what does it mean for like SNARK circuits to call each other. So for example, let's say we have this execution. We're calling A with args A. Somewhere in the middle of this execution, it's calling B with args B. And we want to make a proof of such an execution. So the basic idea is A's public input will contain the verification key of B and the arguments of B. And you may be wondering why is this an issue at all to prove such an execution? Like, don't we have such stuff? And we sort of do. Like, what's a little different in the Aztec scenario is that the functions are already individually snarkified. So A has VKA, B has VKB, and we're expected to use those keys. Okay, so here's what this could look like. So we'll construct a proof for A, called the proof pi A, where the public input now contains the arguments to A, but also the verification key of B and the arguments to B. And now we'll construct a proof for B, where the public input is just the arguments to B. And we'll have a verifier check the proof for A with key VKA and public input XA. We'll have the verifier also check proof pi B with verification key VKB and public input XB. And since this V will use the same args B and VKB for checking A and checking B, this corresponds intuitively to A calling B. That's the basic idea. Okay, But now we want to massage this to a more uniform form. So we want to think of these different steps as iterations of the same function. So we'll have this function f, where the inputs of f are the current vk, the current public input, which again consists of the current arguments of the current function, the next verification key, and the next arguments. And by the way, this is sort of an arbitrary choice for simplicity, that like the current function is calling at most one other function. It might be even more natural to think of it as calling several. In the code, it's 4, the maximum. And also, another argument of f is the current proof, pi, and the current stack of functions to be called. And now what does f check? So it checks that the element at the top of the stack is the current vk and the current args, and it'll pop it off the stack. It'll check that the proof pi with public input x and the current vk accepts. And it'll push to the stack, to the top of the stack, the next function, the next vk and the next args. Another sort of simplification here for presentation is, so here it looks in step 2 that pi is like a full SNARK proof, and we're verifying a SNARK proof. In the actual protocol, the step 2 is just what's called folding a proof of correctness, or really just folding the witness. So, like, if you want to make it closer to what's actually going on, pi is, you can think of it as just as really as a witness, as the actual original witness. Yeah, but for simplicity, you can also just think of pi as a proof. All right, so this is just this f is like a way to, when we have a sequence of calls, just a way to think of those and in each call is right for a totally different function potentially, right? Because different contracts have different functions. But this f is like a way of thinking of this, process of one function calling another is just iterations of the same capital F. But we so far forgot to deal with global state. In addition to functions, a contract in Aztec will have notes representing its state. For example, the notes N1 and N2. And in addition to calling other functions, a function, while it's executing, can add, read, or delete notes of its contract. So to enable these global state operation, we'll add to the public inputs. So far we had the current arguments, the arguments and the VK of the function you're going to call next maybe. We'll also add to the public input the note operations you're doing. So for example, here, like the call to A and these operations, they will have timestamps. So for example, here, the call to A is reading note N at timestamp 8. And the call to B is creating or adding note N at timestamp 3. And now the problem to deal with is, so when we're verifying the proof to A, we see this node operation, read note N at timestamp 8. But while we're verifying this proof, we can't be sure that in some future IVC iteration, we'll indeed see the node N created, and moreover created with an earlier timestamp. Right? We don't want to read notes that haven't been created, and we also don't want to read notes at an earlier timestamp than when they were created. So at a higher level, the order of proving here is different than the order of execution. Since, like I said before, the functions have already been individually snarkified, right? In execution, we start with A, go into B, finish B, go back to A, finish A. But since the functions are individually already snarkified, we have to prove it in a different order. We have to do all the proof for A, and then all the proof for B. So in execution, the node N was created before it was read, but in proving, we're only going to get to that creation of the node N later in the proving process. So to conveniently deal with this setting, we define the notion of RCG, Repeated Computation with Global State. At a high level, or even a less than high level, RCG is very similar to Incrementally Verifiable Computation, IVC, which you've probably heard of a lot. But there's two differences. So the first difference is that in RCG, we know the endpoint. The computation ends before proving starts. So if in the original IVC paper, Paul Valiant is talking about a computation humanity is going to be doing for generations, here we're assuming the computation has ended before the proving is started. So then, well, you could say, okay, so then is it like IVC at all if it's already ended? So why is it even similar? So the desirable property in IVC is what people, they call complexity preserving sometimes, that the prover memory, even if the computation has many steps, the prover memory depends on the memory of the one step. For example, one execution of this function capital F we had below. So in RCG, we still want to sort of have that property, but we relax it. So we say the prover memory should mainly depend on the memory for one iteration, but it's also allowed to depend on the size of the global state. So let me walk you through a simplified version of the actual definition. So we're going to have, to define an RCG relation, we're going to have a transition predicate and a final predicate. And now we're going to say these transition and final predicate, they define the relation of pairs XW, where X, so what is X? X contains the final proof, the final state, sort of, Z final, and the number of iterations N. And W contains 3 vectors, Z, W, and S, where intuitively, Z is going to be the different states we go through. W is going to be the witnesses that get us through those states. And the S's are the chunks of the global state we use in each iteration. So we say that XW is in the relation if, well, we end, Zn is Z final, so we end in the desired final state. For each I, the transition holds, so f of Zi minus 1, Wi, Zi, Si is valid, is accept. And the final predicate, if we insert into it all the S's from all the iterations, it outputs accept. Right, so this third thing is like where we have this additional ability that we wouldn't have in IVC. We are allowed to test some final predicate of little, we think of them as relatively little chunks from all the iterations. And again, the point is, you could just say, okay, just build a SNARK for this relation. Why do you call it RCG? Just build a big circuit. And again, the point, the IVC-like kind of point is, we say a SNARK is space efficient if the prover requires space. I'm not formally define here the size of f, but requires space, which is roughly the size of one step plus the size of the global state. That's the memory that we allow the prover to use. So, like I said, this is a simplified definition. I will raise one little hole in this simplified definition that maybe has occurred to some people here. Maybe we want to hide the number of iterations when we do the zk-SNARK. So in the actual relation, this n is not part of the instance x. What's part of the instance x is some bound c on n, and n is part of the witness. Yeah. Okay, so to illustrate this point, so let's see how we use, an example of a sort of RCG to deal with these memory operations. We're going to add to the add operations. We're going to add the number of times. By the way, if you don't have deja vu, is because I prepared these slides according to previous talks of Jens. So we're going to add to the add operations the number of times a note was read. So that's this numReads field. We're going to add to the read operations we have the timestamp where the note was read. We're going to add to the read operations the timestamp where the note that's being read was added. So that's this AT. And now what are we going to check? So in the transition function, we're going to check for each read that AT is smaller than T, that the alleged time of creation of the note was smaller than the time we're reading it. And now we're going to sort of use the fact that we're allowed more memory in the size of the global state. So the prover is going to store all the node operations from across the iterations. And it's going to hash them to get some challenge beta. And so now, right, so our goal is to check that every time you have a read, you're reading a note that was really added and also added at an earlier timestamp. So this check AT smaller than T sort of checks that if this node is legit, that the timestamp of addition is smaller as needed, but right, it could be that when I have this read NATT, it could be that there actually does not, I'm not going to have an operation add like NAT. It's just, so we need to check that all the alleged creations of notes really happened. And that's going to be done by this fractional sum. So, right, we're going to check that the sum of the reads of this expression, think of the node as just a value in the field. We're going to have this sum over the reads of 1 over n plus beta times AT, the alleged time of creation of the nodes. And we're going to compare that to, we're going to sum now over all add operations from all iterations. And we're going to compare that to now, for each read, we put in the numerator the alleged number of times the note was read, and we divide that by n plus beta times t, plus the timestamp of the add. And you can see that if some attempt to cheat was made, like there's a read operation for a note that doesn't exist, then with very high probability over beta, this sum won't be equal. Okay. Okay, so that's some details from the construction, and I want to end by highlighting a theoretical issue that I think could benefit from scrutiny. So in this paper, to make our proofs easier, or easy, or at least easier, we use what I call the recursive algebraic group model that was implicitly introduced in this paper, Analyzing Nova by Li and Seo. I hope I'm saying that right. And let me explain to you what this recursive algebraic model is. So let's talk about the original AGM. What was the idea there? The idea there is that if I have some structured reference string of elements of the group, then when an adversary outputs some A in the group, they must also explain how they got to this A by the SRS elements. So they must output also a vector of scalars C, such that this A is equal to some CIVI. Okay, But now let's say these group elements, we're representing them as pairs of field elements. So fix some representation function of G by pairs of field elements. And now suppose that the algebraic adversary outputted this vector C, and it just so happens that for some two adjacent indices in this vector of scalars C, Ci plus 1 is a valid representation of some group element B. So you could ask, you could ask, well, shouldn't the algebraic adversary now also give us explain to us how he got to B using the SRS? And some would say, no, you shouldn't do that. But the recursive algebraic group model says, yes, you should definitely make the adversary's life a bit harder and your analysis a bit easier. And yes, you should you should demand an explanation of how to also make B from the SRS elements. So the recursive algebraic adversary now must also output C prime such that B is some C prime IVI. And then you ask, well, what if C prime, there's some two indices that are a valid, does he have to do it again? Yes, that's why there's recursive in the name. So the recursive algebraic adversary must keep outputting these vectors of scalars C until his output vectors with nothing there, no two adjacent elements there are. Right, and as a sanity check, you could say, well, won't he always by accident, there'll be some Ci plus 1 like this and there'll be an infinite loop? Well, it shouldn't be, because, right, if F and G are of similar size, in the elliptic curve case, it shouldn't happen by accident that, So this is the question I want theoreticians to look at, because I really like writing proofs with this thing for IVC. So I want people to look into, is this legit? And yeah, so that's sort of a shout out for that. Yeah, and so thanks for listening. Thank you.
Thank you very much, Ariel. We have a bit of time for questions, if you have any. One over there. Oh.
Hi, Ariel. Great talk. In the recursive AGM, algebraic group model, is it necessary that Ci and Ci plus 1, they are consecutive? Like, it could be any two.
Yeah, that's a great question. It is a little ad hoc to look at all adjacent pairs. The reason why you can't look at all subsets is there's an exponential number of them, and then you will be in a situation where, just by chance, something is a representation and the adversary will be in an infinite loop.
Any other questions? All right, so let's thank our speaker again.